Hello wonderful person, this is Anton, and today we're going to discuss the idea referred to as Milankovitch cycles, a phenomenon that scientists believe is responsible for cyclical climatic changes on planet Earth, and that for the past few million years influenced the formation of things like, for example, glaciers and the periods we sometimes refer to as the Ice Age periods, as well as resulted in additional changes such as increased or decreased precipitation and the expansion of deserts like the Sahara. And this is of course something we've known for a long time. For millions of years, Earth's climate has shifted between long frigid ice ages and much milder, shorter and warmer periods referred to as interglacials. And today we actually think all of this is governed entirely by other planetary bodies, or essentially by subtle nudges here and there and periodic shifts in our planetary movement when it comes to its orbit around the Sun. And so it's these orbital variations that we refer to as Milankovitch cycles, named after Milutin Milankovitch, who provided a definitive proof for this back in the 1920s. And today we know that these cycles definitely play a huge role in the climate on the planet, and especially in something referred to as climatic forcing. They change the distribution of solar radiation on the planet, which can then dramatically affect certain areas in just a few hundred years. But for decades, many studies in regards to this were focused on, obviously, the Sun and larger planets like Jupiter and Saturn. As in, most of this is very likely caused by Jupiter, but obviously not everything. And it was really some of the recent and more detailed studies that started to uncover that there's also something else going on here. And specifically, as you can probably tell from the title of this video, much smaller planets like Venus and even Mars seem to play a pretty big role as well. And so in this video we're going to explore some of these new discoveries and what we actually know about this, and specifically focus on this recent study on the effects from these gravitational nudges from our neighbor Mars. But just in case you have no idea what these cycles are and how all of this works, let's do a very brief overview. So how exactly does this work? Well, this NASA link in the description explains this in a lot of detail, but in essence there are really only three components. First we have the eccentricity of the planet. This is the shape of Earth's orbit around the Sun. Is it more circular or is it more elliptical? And so when the orbit is more elliptical or elongated, the variation in distance between Earth and the Sun increases a little bit more. And this affects how much solar radiation Earth gets throughout the year. Today, scientists are pretty certain that this is definitely caused by Jupiter and Saturn. And it seems to manifest itself in a very stable cycle that's about 405,000 years long. And here it actually has three separate periods. And so this much longer stable cycle contains much shorter cycles of around 95,000 and 124,000 years, which loosely combine to create the 100,000 year cycle that we actually observe in a lot of geological data. Then we have something referred to as obliquity. This is essentially the Earth's rotational axis. Now currently the axis sits at about 23.4 degrees, but as you can see here it varies between 22.1 and 24.5. And this takes approximately 41,000 years. And so here a graded tilt results in more extreme seasonal temperature variations and thus more extreme weather, whereas the decreased tilt promotes milder seasons, but also encourages a cooling trend, which actually can create a glacial period during this time. And that's mostly because there is less sunlight in the summer, and so at very high latitudes it becomes very difficult to melt previous ice and to warm up the ground. And then we have the wobble or the axial precession. This essentially makes Earth kind of similar to a spinning top. And this cycle is about 25,700 years long and generally affects which of the hemispheres ends up getting more sun, especially when Earth is super close to the Sun. And so this drives seasonal extremes, and combined with other cycles can also create an additional primary cycle of 21,000 years. And so altogether, these cycles define Earth's solar forcing, shaping glacial and interglacial periods that have dominated Earth's history for the past 2 to 3 million years. But apart from changing the amount of sunlight, these cycles also do something else. For example, one major historical puzzle here is sometimes referred to as the 100,000 year problem. And specifically here, although the 100,000 year cycle seems to dominate variations in ice volumes on the planet, at least over the past 800,000 years, generally, orbital eccentricity contributes much less to changes in solar radiation compared to other cycles. And so there's actually a bit of a discrepancy in how much sunlight Earth is getting and by how much ice seems to decrease and increase every 100,000 years. And so here this discrepancy suggests that Earth's climate system contains a lot of internal feedback mechanisms, most likely associated with levels of CO2 and potentially other greenhouse gases that essentially get released or get trapped inside during certain events caused by these cycles. For example, even just a little bit more sunlight may actually start thawing a lot of permafrost, which can then start releasing a lot of methane and dramatically decrease the levels of ice in a relatively short time. Furthermore, additional studies from the last few years highlight that a lot of these climatic changes don't just affect the levels of ice or affect the rain, for example. They seem to be also linked to Earth's internal processes such as volcanism. This was actually reported in one of the recent studies you can find in the description, but turns out that variations in global climate, and specifically advances and retreats of massive ice sheets, which also result in very different sea level changes, seem to physically modulate volcanic activity on relatively long timescales of thousands to tens of thousands of years. Or just to rephrase this, volcanism seems to be also directly affected by a lot of these cycles, and specifically by the movement of glaciers. So for example, the retreat of glaciers or glacial unloading reduces the pressure on Earth's crust, which can lead to decompression melting in the underlying mantle. And this actually dramatically increases the rate of volcanoes, and thus increases the amount of stuff being released by volcanoes long term. And so by having less glaciers, we actually get more volcanism, which then starts to cool down the climate long term because of all of the gases released from the volcanic eruptions. And this is not just a hypothesis, there's actual evidence. Milankovitch cycles of 23, 41, and 100,000 years seem to appear directly correlated to global volcanic activity, suggesting a direct connection. So essentially, these cycles seem to play a much bigger role on planet Earth than we ever expected. But once again, the foundation for these cycles is of course the result of gravitational interactions with a lot of solar system bodies. But scientists never really thought it's going to be smaller bodies like Mars and Venus. And so now we have this new study that reveals that Mars seems to exert a particularly strong and often surprising influence on the planet that was previously ignored. And so here, by using computer simulations and models, and by essentially varying the mass of Mars compared to other planets, and then tracking the resulting changes in the Earth's orbital evolution, scientists were able to discover exactly what Mars's role seems to be. And so first of all, here the simulation officially confirmed that the most stable cycle is approximately 105,000 years. This is once again mostly driven by the larger planets. As a matter of fact, the cycle persists independent of other planets, just because Jupiter is the most massive planet in the solar system. But surprisingly, almost every other cycle seems to change dramatically if you actually change the mass of Mars. And so here, by changing the mass of Mars from 0 all the way to 1000%, scientists discovered that the orbital changes on planet Earth seem to actually be quite extreme. For example, when it comes to the cycles responsible for the ice ages, the 100,000 eccentricity cycles seem to actually heavily rely on Mars's gravitational presence. And so in the simulations, as Mars became more massive, a lot of these 100,000-year cycles lengthened and gained power. Alternatively, when Mars's mass was 0, these cycles weakened and became almost insignificant. And so this potentially suggests that one of the main reasons we might even have ice ages is because of Mars. But here this was not even the most surprising discovery. The most striking discovery was of a much longer cycle, 2.4 million years. This is a very long-term climate fluctuation and is a kind of a grand cycle when it comes to eccentricity, and it seems to be tied to the slow rotation rates of Earth's and Mars's orbits and disappears entirely when Mars is 0 mass. We've actually briefly discussed this in one of the previous videos in the description, but basically here, Mars seems to create an actual new cycle on the planet that we've never really known about before until some of the more recent studies. And so this grand cycle of 2.4 million years only exists because of Mars, and only because it seems to create the right gravitational resonance with our own planet. And obviously our planet seems to influence Mars as well, so it also has its own climate changes because of Earth. And then the last cycle, the Obliquity cycle, seems to be also sensitive to the Mars's mass. Here the familiar 41,000-year cycle seems to lengthen as Mars becomes more massive, with simulations showing that if Mars was 10 times as massive, the 41,000-year cycle would shift becoming the dominant cycle and dramatically changing the climatic changes on the planet roughly around every 45,000 years. This would actually dramatically alter the patterns of ice sheets and possibly even cause Earth to become an ice planet. And so in many of these experiments, scientists demonstrated that the mass of Mars seems to be the main controlling factor in driving a lot of Earth's climatic shifts because of these Milankovitch cycles, with these findings showing us that Earth's Milankovitch cycles are not just a product of our planetary dance with the Sun and Jupiter, but is definitely a result of a lot of planetary interactions with pretty much most of our neighbors. And this is of course important for at least two main reasons. First, understanding these predictable climatic changes helps us establish highly accurate baselines for what we naturally expect to happen on the planet over the next few thousands of years. For example, studies using this knowledge predicted that the next ice age should occur in about 10,000 years from now. But by establishing these natural baselines, we can now start quantifying when it's actually going to happen, because of obviously human emissions and a lot of additional climatic changes in the last couple of centuries. So for example, we know that additional emissions of carbon dioxide and huge amounts of methane, both natural and artificial, seem to have already diverted some of this climatic shift from its natural course. But at the moment it's unclear if human-made climate change is going to completely prevent the next ice age from happening, or if it's just going to create some kind of a freak weather every year, as a lot of additional mechanisms on the planet try to basically rebalance themselves and force the climatic changes to continue into the ice age despite all of these greenhouse gases. So basically right now nobody actually knows what's going to happen, but this is why these studies are kind of important. And then at the same time, a lot of these results also obviously tell us a little bit more about exoplanetary habitability. Because by studying these Milankovitch cycles, we learn about interplanetary interaction and various planetary changes, and learn to understand how a lot of these Mars-type perturbers may shift certain cycles, producing slightly different exoplanetary architectures. And so, for example, if we do discover some kind of an exciting planet out there, for example, maybe in the TRAPPIST-1 system, we have to then start understanding how the additional 6 planets in the system influence that one planet that we now want to understand. And for TRAPPIST-1 system, where all of the planets are pretty close to each other, the Milankovitch cycles there would be pretty extreme. And so the main point here would be finding planetary configurations where we can, in theory, have a very stable climate long term, without any major shifts. And so for example, when we look at Mars, we know that Mars is definitely not the right planet. And that's because over time Mars tilts its axis by something like 60 degrees. Which essentially means that this particular planet would just not have stable conditions long term and would unlikely to have habitable conditions for a very long time. And so here we're looking for a terrestrial planet orbiting a distant star, but that seems to have very similar orbital configurations and only experiences very mild climate variations that prevent dramatic freezing or dramatic runaway of various gases. And basically it does have seasons, but nothing extreme, because based on Earth, we think that this is what's conducive for complex life. But ultimately, based on this new study, we now have pretty strong evidence that even the humble Mars, which is very often overlooked when it comes to orbital shifts, seems to play a surprisingly important role in shaping the seasonal rhythms on our planet. And so here we're talking about the ice ages and the long-term stability of the entire planet. And that by itself is of course just a little bit surprising. But once we actually learn something else, or once there are some additional discoveries about the Milankovitch cycles, we'll come back and discuss this more in some of the future videos. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.